So welcome to today's session, which is session 9. We're going to focus on functions. But first we have a quick announcement. Basically, we're going to have a workshop. Like, we invited someone to come on and give a short 1-hour workshop on set theory. His name is Mr. Yul In. He is a native of the area. He is the founder of the Fun Math Club, which is a math circle he runs for like middle school students in Cupertino. And he's also a math circle lecturer at Stanford, and that's how I met him. So he's gonna come over and he's been very gracious that he could like present about set theory. He can come on January 22nd, which is a Friday, but we do need to know which time to ask him to come over. We know that a lot of people in this class are in very different time zones, so if you could let us know what time works for you, you should have gotten an email asking the same thing. And the sooner we get an answer for him, the better. Could you let us know in the chat like what time of day after 4 p.m. on January 22nd would work for you for a 1-hour workshop? Okay. Alright, we'll keep that in mind. And I think we can get back to the lesson now. It was really short.
Okay, so today the concept that we'll be discussing is the concept of functions, but in terms of set theory. So a function is simply a triple of objects or three, or can be expressed in three objects: the function or the f itself, a and b, where a and b are clauses, and of course whatever applies to clauses applies to sets, because sets are just a type of clauses. And f is a subclass of a cross b. So you know already that f would be an ordered pair where the first element belongs to a and the second element belongs to b. But it's a special kind of subclass because it has to admit to two conditions. First, that for all x belongs to a, there exists a y that belongs to b such that xy belongs to f. So that means that every element that belongs to a must have a corresponding element that belongs to b. Okay. And the second condition is that if x, y1 and xy2 both belong to f, then y1 equals y2. Or that you cannot have more than one image for the same element. So these concepts will become clearer as we describe what an image and a pre-image is. So the two elements, so if x belongs to a and y belongs to b and f maps from a to b, then you would have that x is called the pre-image of y and y is called the image of x. Okay, and another way to notate f from a to b instead of this notation or the triple notation, we'll just use this notation. So f maps from a to b. So these two conditions would just translate to that first, that every element in X must have an image in every element in A must have an image in B, if we are speaking of functions, and the second condition said that this image is unique. You cannot have more than one image for it to be called a function. Okay. So this is a concept that should have been explained with graphs already, but we delayed it to functions because it's dominantly used with functions. So first you have that the domain of G is defined as this class. So already the domain and the range and all those things are classes. So the domain of G, where G is just any arbitrary graph, and of course this also applies to functions, so you can speak of the domain of functions in the same manner. So the domain J equals X such that there exists Y, where X and Y belongs to G. So the domain of G is just simply if you have an ordered pair of X and Y and belongs to the graph, so the domain of G is the set of all the first elements of the ordered pairs, which are all just all these elements X. So if you have a class of ordered pairs, so it's just x1, y1, x2, y2, etc., and they all belong to a graph G, then the domain of G is just the class of all the first elements in all these ordered pairs, or x1, x2, x3 to the end. The range of G is just the opposite of that, so it just equals y such that there exists an x, such that x and y belongs to G. So it's just the class of all the second elements in the ordered pair. So these So this is when we say the domain of G, that's what we mean. We mean if you have an ordered pair in any graph, and this includes functions because functions is just special kinds of graphs, then you just take the first element from each ordered pair and you form a class. This class is called a domain. And the opposite for the range, you just take the second element of every ordered pair in the graph and then you call it the range of G. Okay. So these are some theorems, and these are relating to functions. And these theorems just show why a function is a special kind of graph, or what specific conditions you can find in a function, but do not find in every graph. So if you have A and B are classes, and f is a function that maps from A to B, these three are always true. The domain of f is the same as A. The range of f is a subclass of B, but not necessarily equal to it. And you have f equal g if and only if an x equal g of x for all x. So the notation of y equals f of x is just the same as saying xy belongs to f. So instead of saying xy belongs to f, we usually say y equals f of x. So you should have some time to think of these three, and then we'll display the proofs of these and why they are true. Okay, so for the first one, the first theorem that the domain of f equals a, so we start with the standard way that we assume that there is an arbitrary element x belongs to the domain of f. So from the definition of domain that we just gave, this implies that there exists a y such that xy belongs to f. Okay? And we said in the definition of functions that f is a subclass of a cross b. So if x and y belongs to f, then x and y belong to a cross b. But if x and y belongs to a cross b, this would imply that x belongs to a. And of course y belongs to b, but the second piece of information is not it's not of importance here. So if x and y belongs to f, then x and y belongs to a cross b, which would then imply that x belongs to a. But again, for equality, you must be able to work in reverse. So what will not say that even though if x and y belongs to f, this would imply that x and y belongs to a cross b, the opposite is not true. You cannot assume the opposite. And so we will have to work in a different way to prove that if x belongs to a, then x belongs to the domain of f. And this would be that if x belongs to a, then from the definition of function that we gave before, then there exists a y that belongs to b, such that x and y belongs to f. So that's again from the definition that we gave before, when we said that if you have if for every element in A, there exists an element in B. So just back to the definition of functions. For all x belongs to A, there exists a y belongs to B, such that xy belongs to f. So that's from the definition of the function. And so I can say that if x belongs to A, then there exists a y belongs to B, such that x and y belongs to f. And this is just again the same definition as of the domain. So I can say that x belongs to the domain of f. And so if I have that there is an element that belongs to A, then it belongs to the domain. And if an element belongs to the domain, then it belongs to A. And this implies that these two are just equal. That's just from the definition of equality. Yeah, if I know that there's an element in domain of F, then this element is in A. If I know that the element is in A, then the element is in the domain of F. The second theorem, that the range of F is a subclass of A, using the same standard way, if y belongs to the range of f, this would imply that there exists an x such that xy belongs to f. So this again from the definition of what a range is. And from the definition of a function, I know that f is a subclass of a cross b, then this would imply that xy belongs to a cross b. But then y would belong to b, and this f should be removed. It's just y belongs to b. So the reason why this is only a subclass, this also the range of f is a subclass of b, not a. Okay, so this is a typo here. This should have been b. So why we cannot work in reverse? Because the definition of a function guarantees that every element has an image, but it does not guarantee that every element has a pre-image. And so in this case, we could work in reverse and say if x belongs to a, then there exists a y. that belongs to B such that xy belongs to F. However, the opposite is not included in the definition of function. So if there is x belongs to B, this does not guarantee that there exists a y that belongs to A such that x and y belongs to F. Because if we go back to the definition of a function, this is one of the conditions that for all x in A, there exists a y in B. However, we have no condition in function that says for all y in B, there exists some x in A. And that's why in the domain, we were able to work backwards. However, in this case, we will not be able to work backwards. That's why we can only say that it's a subclass of B. Again, as I said, this should have been B. That's a typo. Okay. So the range of F is a subclass of B. And so it can be equivalent, but it's not necessarily equivalent. And this point will be important as we explain different kinds of functions. The third one, the third theorem, that F equals G, or that if you have two functions, F and G, they are equivalent, if and only if fx equals g of x for all x. So we will assume first that f equals g, then we will assume that fx equals g of x, and we'll show that these two lead to each other. So first, let's assume that f equals g. So I have that if y equals f of x, so y is just an arbitrary element and x is an arbitrary element. So I'm saying that if y equals f of x, this just means that xy belongs to f, because as we said before, it's just a different way of writing it. If xy belongs to f, this is the same as y equals f of x. So if y equals f of x, this is the same as xy belongs to f. So in this case here, if I have y equals f of x, then xy belongs to f, right? And I have that f equals g. And since f equals g, then if there is an element in f, then it's also in g. So since xy belongs to f, xy would also belong to g. And this is just the same as y equals g of x. So if you look at what we have proved here, we have proved that if y equals f of x, then y equals g of x. And this is the double arrow, which means that you can work in reverse. So if I start with y equals g of x, this means that xy belongs to g. And since g and f are equivalent, then I have that xy belongs to f, which would then mean that y equals f of x. So what this proves that f of x equals g of x for all x. Now we will assume the other condition. We'll assume that let f of x equals g of x for all x. Then I can say that xy belongs to f, imply that y equals f of x. And I know that f of x equals g of x. So the fact that xy belongs to f implies that y equals f of x, which equals g of x, which would then imply that xy belongs to g. And this, of course, works in reverse. If xy belongs to g, then y equals g of x, and g of x equals f of x. Then y equals f of x, which would mean that xy belongs to f. And so if I have an ordered pair in f, then it also exists in g. And if I have an ordered pair in g, then it also exists in f. We just prove that f equals g. And so these two results combined prove that if I have that f equals g, then f of x equals g of x. And if I have that f of x equals g of x for all x, then f equals g. And this is just the proof of the third theorem. So now there are certain special kinds of functions. So you can notice already that you have a graph or an ordered, you have the Cartesian product of two classes that these form a graph, and you have the special kind of graph that's called functions, and then we'll have a special kind of function. So we're just adding conditions, and when we are adding conditions, we keep the older ones. So all the conditions that apply to the graph apply to the function, but the function has extra conditions. And all the conditions that apply to the function applies to all the different kinds of functions, but we'll add extra conditions. So what an injective function is, it's just that if fx of 1 equals fx2, this implies that x1 equals x2. What this is saying that every pre-image would have a unique image. Okay. So this is different from the definition of function. The definition of function said that every image has a unique pre-image. This now is saying that every pre-image has a unique image. So that's an additional condition. And so as an example, if you look at these two charts, this is not an injective function because you have these two red elements here, they share a common image. And these two elements here, they share a common image. So this is a function because every element in A is paired with something. But now you have these two elements paired with the same thing. So this is not injective. However, in this case, you have that every element in B is paired to only one element of A, right? And of course, you can have some elements that are not paired because, as we said, the range of the function is only a subclass of B, so it's not necessarily equal to B. However, what is necessary for a function is that you have every element in A is paired with something. So you must have every element in A paired with something, or else the function is not from A to B. It can be from a subclass of A to B, but for it to be a function from some that maps from something to another thing, you must have that the domain is equivalent to A, or to this class right here. So this is just what, and so you can just say that injective function saying that for every pre-image, every pre-image has a unique image. Okay. Then there is surjective functions. So, oh, surjective functions, all they are saying that the range of f is the same as b. So so for every element in y, it is paired with something in x. Okay, so for this example, right here you have the class x. It has elements 1, 2, 3, 4, and the class y has elements d, b, and c. So 1 is paired with d, 2 is paired with b, 3 and 4 are both paired with c. So you can already see first that it's not injective because you have here two elements that share a common image, but you can see that every single image, every single element in y is paired with something in x. That's different from here when we had like these two blue elements here, they were paired with nothing. So you did not pair every single element of y with an element of a. And here you have every single element paired. And one last thing, that injective functions are sometimes called one-to-one functions. Surjective functions are sometimes called onto functions. So the last kind of function is just a combination of both, and it's called bijective functions, or sometimes called one-to-one correspondence. That's different from the injective. The injective is one-to-one function. Bijective is called one-to-one correspondence. So this is just simply both injective and surjective at the same time. So this means that for every element in X, you can pair it with element in Y, and you will have no left-offs at all. So you can, so here 1 is paired with D, 2 is paired with B, 3 with C, and 4 with A. So you have no element in Y that's not paired with an element of X, and certainly from the definition of function, no element in X that's not paired with an element of Y, and every element in X is paired with at most one element in Y. So it's paired with exactly one element in Y. So this is just what a bijective function is. So it's just a combination of the last two types of functions. So you just add the two conditions of the injective function and the surjective function to get a bijective function. So these are some examples of functions. So first, the identity function of a certain class A. So first, this function maps from A to A, so it maps from a class to itself. And what this does is that I of x equals x. So the image and the pre-image are just the same, and that's for all x in A. There's the constant function k of x equals b. So for that's for all x belong to A. So the constant function maps from two classes, A to B. And the last type is the inclusion function, or the last example of functions is the inclusion function. So first we'll let B and A are classes. So we are assuming that A and B are classes in all the cases here. Let B be a subclass of A, and A maps from B to A. Okay, so the domain is in B and it maps to A. What this is saying that E of x equals x for all x belong to B. So how is this different from the identity function? They are the same if and only if B and A are equal. So if B equals A, then you'd have the inclusion function is the same as the identity function. However, however, that's not necessarily the case, because what's happening here is that you have the class A, then you are taking a subclass of it. So within this subclass, every element of X is paired with itself. But this is not necessarily the case inside A, but outside of B. So what this is saying is this is just the same as the identity function, but it does not apply from A to A itself. It applies from a subclass of A to A. So we're just changing the domain. So the same as the identity function, but with a different domain. That's the only difference between the identity function and the inclusion function. So try thinking of which of these is bijective, injective, surjective, etc., and type it in the chat what you think of each of these two. So, so going to just proceed with the answers, I guess. So the first one, the I of x is bijective. First, the reason why it's injective is that if you have ix equals iy, first ix equals x and iy equals y. So if ix equals iy, then x equals y. And so then you have, and you can see that, or you can make it ix1 equals ix2, then x1 equals x2, which means that then it would be injective. So that's the first, the idea of it being injective, and for the idea of it being surjective, because now you know that if x belongs to A, then ix belongs to A, but then every element, uh, but then x forms all the elements of A, and ix equals x, so there is equivalent number of x's as much as there are of ix, and you have, and you know from the definition of function that every element in A is paired with something. So if every element from A is paired with some unique element, because we said that it's injective. So first, with the fact that it's injective, then for every element in A, it's paired with at most one element in A. And you know that there is as much elements X as much as there are IX, because they are both equivalent. Then you can see that every element in A is paired with another element in A, or with the same element actually in A. So you can say that every element in A is paired with something. So that makes it subjective and injective at the same time. So it's bijective. For the second one, the kx equals b, first, you cannot say that it's injective because every single element is paired with the same image. So it's definitely not injective. Except in one case, if A has one element, then it can, then in this case it will be injective. But in any other case, if A has more than one element, then you already know that all this element is paired with the same image, which is just not injective at all. That's exactly the contrary of the definition of injective. So the only case when K effects would be injective if you have only one element in A. And this kind of the same thing with surjectivity. You know that every single element is paired with the same element in Y. So if you have more than in B, so if you have more than one element in B, none of them is paired except just one element, which is the constant that you have here. So so you can think of already, if you can, if you go back for something like this image. So just ignore all the elements that are currently here. I just want the oval shape. Imagine a lot of elements here and a lot of elements here, but all the elements here are just paired to one of these elements. Then first you know that it's definitely not surjective because every element in Y is not paired with anything except this one element, and it's not injective because all the elements in X are paired with the same element. So you can say that the only case it can be surjective if there's only one element in B, which is this constant right here. And the only case it will be injective if there's only one element in A. And so the only way it can be bijective is that if both A and B, each of these has only one element. So so in general, you cannot say that it's injective or that it's surjective. So it's none of these three. And again, you can have functions that are none of these three types. That it's neither injective nor surjective, no, and definitely not bijective. You can have those elements. You can have those type of functions. So so even though you cannot say that this element is certainly injective, it can be injective in the case that there's only one element in A. And it can be surjective in the case that there's only one element in B. For the last one, it's definitely injective because every element in B is paired with itself. It's not necessarily surjective. The only case it will be surjective if B equals A, because then we'll be with the identity function, which is surjective and injective. And the reason why this is subjective, you can just imagine two circles. So a bigger circle and an inner circle. So the inner circle is just B. So every element in B is paired with itself. So but now we can see that every single element that's not in B but in A, so every single element that is in the outer circle but not in the inner circle is paired with nothing. So it cannot be surjective. The only case that this can be surjective if the two circles are the same circle, or if B equals A. So I hope that the answers to these questions and why they are injective, subjective, or none of these was made clear because we'll need this in the exercises. So this is just the first exercises. The first exercise. So describe with either subjective, injective, bijective, or none of these. So these are already some arithmetic functions that we are used to. And an important point when dealing with subject with the idea subjective, injective, bijective, you can have a function that can be injective and not injective in another case, and that depends on the domain that you're dealing with. So when you are deciding whether it's injective, subjective, bijective, or none, you should look at the domain and the range of the function, because all what subjectivity is talking about. So when you are dealing with a subjective function, it means that the range, as we said, that the range equals the second class or B. And so if I change the range, it can be subjective in some cases, and it can be not subjective if I change the range in another way. And that's why before deciding, you should look at the domain and the range of your function. So you should proceed with these exercises and type the answer in the chat for these 3 ones right here. Okay, so the first one is first injective because you can just plug in any value from the R positive into the X and it will have an image. And is surjective because we're defining it over the R positive. So why here we need to look at the domain and the range? Because just imagine if this R positive was R, then it would not have been injective because you can have negative 2 squared equals 4 and 2 squared equals 4. Then you would have two separate elements and they are mapped to the same value. Then it will not have been injective. And that's why when we change the domain into R positive, so only the positive real numbers, then you would have that it's injective because x squared would always have a unique solution over R positive. So and it's surjective because you can get any real number out of the square of the real number that you have. Or whatever value you can give me. So let's say if x equals 4, I can find an x. You can take just the square root of this 4 and it gives you the x that you have. And we are only dealing with positive values because the domain is R positive. So it's both injective and subjective. The second one is f of x equals x power 3 from z, which is set of integers, to the set of integers. This is first injective because every single one would have a unique solution. However, it's not surjective because, for example, say if x equals 3, so is there any way that the function can be equivalent to 3? And the answer is no, because the only solution for x would be cube root of 3, but cube root 3 is not in the domain. And so this function is injective, but it's not surjective. Because there are certain values in z that you cannot get by this formula, like 3 or 2. So the f of x would only have the values of the cubes. So 1 power 3, 2 power 3, 3 power 3. So there are values in z that are not included in the f of x. And then so this function is not surjective, however it is injective. The last one is also bijective because first you can plug in any real number into x plus 1. So this is defined all over, and it will have a unique solution. So the important point is that it has a unique solution. Okay. And the second idea and the second point, why it's surjective, can get any real number out of this. Because if you sketch the graph of something like 2x plus 1, you'll find that it's a straight line. And this straight line extends from negative infinity to infinity. So you can get any number on this line. So it's both injective and subjective at the same time. The second question or the second exercise. So prove that, so f here is a function, is defined by this ordered pair x and the ordered pair of x and x, where x belongs to a. So prove that this is a bijective function from a to I of a. I of a is just the identity function. Identity function for a, so it's just I of x equals x. So this is what I of a means here. Okay. You'd have about 2 minutes to think about it. Okay, so the solution to the proof problem. First, assume that f of x equals f of y. So usually when you are trying to prove that a function is injective, you start with this assumption that f of x equals f of y, and then you try proving that then x equals y. So if f of x equals f of y, well, this means that x equals y. Why? Because this is just what the function would be. So again, we have that the second element of the ordered pair, that's what f of x would be. And so the second element is just the ordered pair of x in itself, right? So f of x is just x, and fy is just y. And so if you have x equals y and y, in the session when we talked about the Cartesian products and the ordered pairs, we said that two ordered pairs are equivalent if the first element is equivalent to the first and the second is equivalent to the second. And so since x and the ordered pair of x and x equals the ordered pair of y and y, then x equals y. And you can again work in reverse. If x equals y, then the ordered pair of x and x equals the ordered pair of y and y, then you would have f of x equals f of y. That's for the injective functions. For the surjective, so what we want to prove that there is no single element in your function, in the range of your function, that's not paired with something. Or, and this is logically equivalent, and when I say logically equivalent, it means that if this is true, then this is true. If this is false, then this is false. This logic equivalent is saying that if there is any ordered pair that's not in the range, then it's not in the domain. Okay, so this would just mean that every element that's in the range, it has a corresponding element in the domain. So if I say that everything that's not in the range is definitely not paired with anything in the domain, this just exactly the same as saying that for every single element in my range, I have a corresponding element in the domain. Uh, these statements are called contrapositive statements, or just logically equivalent statements. So if one is true, then the other is true. If one is false, then the other is false. Then it would be sufficient to prove that only one of these statements is true. Then the other would logically follow. So in this case, I'm going to assume that there's an ordered pair xx that does not belong to my function, my identity function. Now I know that my identity function is a subclass of a cross a, because that's the definition from the function. And I know that I maps from a to a. So since x and x does not belong to I cross a, then it does not belong to a cross a, which would then imply that x does not belong to a. Because if x and x does not belong to a cross a, then x does not belong to a. This would be a surjective function. However, if you notice in this here, we said that since x and x does not belong to I of a, then x and x does not belong to a cross a, even though I know that I is just a subclass of a cross a. And the reason is that I know that I of a is a bijective function. So this first implication would not have worked unless I of a is a bijective function. And the reason is because if I have two circles and one does not belong in the inner circle, this does not imply that it does not belong to the outer circle. The only case when this is implied is when the two circles are equal. And they are only equal in the case of a bijective function. And so in here, if I have x of x is not equal to I of a, then x of x does not belong to a cross a. And if that's the case, then x does not belong to a. And so what we have proven is that if there is any ordered pair that's not in the range of the function or in the b element, then there is no element x, there's no such element in a. That's what it's saying. So what's saying that? Just a second. And what's saying that if this x and x is not in I of a, is not in the function that I'm mapping into, then there is no such element x in a. Or what this means that for any x that belongs to a cross a, there is an element x in a. Right? So what this is saying that the only case when you do not have something mapping to b is that if this thing is not in a, which means that if you have something in a, then you are guaranteed that it maps to something in a cross a, which means that it's a surjective function. And if it's both injective and surjective, then it's bijective. So that's all the questions.
Cool. I think we can wrap up for today then. And sorry for starting and ending a little bit late. Both of us had like technical difficulties at the same time, but at least it went smoothly. So yeah, thank you for coming. Bye.